In this video, we will learn a new way to evaluate the performance of our models, KFold cross-validation. In the last video, we used statistics that were computed on the training dataset to measure the accuracy of the model that was also built on the training set. In class, we explored using a test set to help us evaluate the performance of our model. The KFold cross-validation method will expand on and improve that method. First, let's review a result we saw at the end of the last video. Recall the model we fit using only 10 car observations. The adjusted R-squared is 1, and the RMSE is virtually 0. The model seems great. As it turns out, we can often get good performance on the training dataset, especially if we make a complex enough model. This is called overfitting. With smaller datasets, it is fairly easy to do this. But even with large datasets, we can also create and add enough variables with enough complexity to overfit the model. In machine learning, we are mostly concerned about predicting future unknown values. So we want to have an honest assessment of how well our model performs on data it hasn't seen. How do we do that? I know. How about using that test data set we held out initially? Although this is what we did in the activity in class, in general, this is not what we will do. There are two reasons. One, the test set error rate could vary quite a bit depending on the particular test set that was randomly held out. And more importantly, two, we want to reserve this test set to compare our final few models, likely after we have tried numerous algorithms to predict our response. Let's look at the big picture of our build, train, evaluate loop again. Just to overemphasize this point, notice again the testing data is left out until the very end. That is what we will use to compare the few best models we have after trying different algorithms. In order to try to find the best model within a specific algorithm, for example, the best linear regression model, we only want to use the training dataset. This process of finding the best model within an algorithm is often called tuning the model. In linear regression, usually what we are tuning is the number of variables used in our model. In other algorithms, there will be other parameters that need to be tuned. So, how do we honestly assess how well our model performs on data it hasn't seen when we are only using the training data? We sample from the training data. Within each of these samples, a piece is reserved for fitting the model, represented by the blue analyze boxes in the schematic, and another piece for assessing the performance of the model, represented by the green eval boxes in the schematic. This process is repeated many times, so we can average the performance over different samples. There are many ways we can do the sampling. Today, we will talk about a technique called KFold cross-validation, or KFold CV for short. In KFold cross-validation, we start by dividing the data randomly into K approximately equal groups, or folds. The schematic here shows 5-fold cross-validation. The model is fit on K-1 of the folds, and the remaining folds is used to evaluate the model. Let's look at the first row in the schematic. Here, the model would be fit on the data that are in folds 2, 3, 4, and 5. The model would be evaluated on the data in fold 1. If we are fitting a linear regression model, that means we would compute the RMSE for fold 1. In the second row, the model is fit on the data in folds 1, 3, 4, and 5, and the RMSE would be computed for the data in the second fold. After this is done for all 5 folds, we take the average of the performance statistic, like RMSE for linear regression models, to obtain the overall performance. This overall error is sometimes called the CV error. Averaging the performance over k folds gives a better estimate of the true error than just using one holdout set. It also allows us to estimate its variability. Although it somewhat depends on the size of the data set, 5 and 10-fold cross-validation are quite common. Next, I will briefly introduce 2 functions from the caret package that will help us do k-fold cross-validation, and some other sampling methods later in the course. We will explore these functions more deeply in class. Caret is an acronym for Classification and Regression Training. The functions in caret can be used to perform many different machine learning algorithms without changing too much of the code. We'll be very thankful for this as we continue to learn more algorithms. The train control function sets up the sampling methodology before the full cross-validation process is executed. For now, we will only use 2 of its arguments. Method is the sampling method we want to use, CV for cross-validation, but we will use others later. And number is the number of folds in cross-validation. Once that is set up, we can move on to the train function, where the cross-validation is actually executed. Since random sampling will be used, we must first set a seed so we can reproduce our results. The first argument in the train function is the model formula, just like what you're used to using in LM. This can include interaction terms and other transformations if you'd like. The data argument will either be the training data after the data have been split into training and test data sets, or it could be a baked training data set after applying some transformations using functions from recipes. The method is the model fitting method or machine learning algorithm. For now, we'll use LM. The TR control argument is the sampling methodology. It needs to be the result of the train control function. NA action equals NA omit will omit any row with missing values. Be careful with this if there are a lot of missing values in the data set. We will use the data on cars from the EPA as an example. First, we split the data into training data and test data, putting 70% in the training data set. Then, we use the train function to do 5-fold cross-validation on the linear model that uses all variables except model and model index to predict MPG. Let's look at some output. The summary function returns standard model output. Unfortunately, there isn't an easy way to get the tidy model output that looks nicer and is easier to work with, but this will do for now. This is the exact same output we would get if we used LM to fit a linear model that uses all variables except model and model index to predict MPG. But the train function also provides the cross-validation error, which we can't get when we only fit the model with LM. The results give the overall results of the sampling process. So RMSE is the average RMSE over all 5 folds. The resample output gives the details for each fold. If you averaged all 5 RMSEs from the resamples output, you would obtain the RMSE in the results output. Sometimes you want to know which observations are in each fold. The output here shows the observations in the first fold. We could find the observations from the other 4 folds in a similar manner. Now you have an overview of k-fold cross-validation and how to implement it in R. But I still don't know which is my best model. How can cross-validation help us decide? That's what we will begin to discuss next class.